In this operations management video, we're going to talk about quality control charts. These are the cornerstone of any quality control program. My students can access the video tutorials for these problems using the content menu in D2L. YouTube viewers can access the video tutorials on my MOOC on udemy.com. I have a long and short version of the URL posted on the screen, and I will post this URL in the description. The purpose of a control chart is to monitor the process output to see if there is assignable variation. Stated another way, the purpose is to make sure that the only variation you're seeing is random variation. A control chart is a time-ordered plot representing sample statistics obtained from an ongoing process. In other words, you're measuring the size of the holes you drill, computing a sample average, and plotting them on a chart. The upper and lower control limits define the range of acceptable variation. This is acceptable to your process. It's not anything to do with the customer's specifications. Here you see a sample control chart. There are three lines: the upper control limit, the lower control limit, and their center line, the average performance. The dots represent the individual observations, the average of each sample of the size of the holes drilled, for example. Anything that's in the blue area is out of control because it exceeds the upper control limit. Anything that's in the yellow area is out of control because it exceeds the lower control limit. For any control chart, you need to calculate the upper control limit, the center line, the lower control limit, and that's calculated once. And then you need to plot the points, and there'll be one for each sample. Some software adds a line between the points, some don't. The line adds no value, so it doesn't matter. All processes have variation, even automated processes, even robotic processes. They all have variation. The variation that they normally have is random variation. The reason we're monitoring the process is to make sure that we only have random variation. There are two types of variation: random and assignable variation. I'll give you a definition in a moment, but first I want you to think about a basketball player, a professional basketball player, one that has a pretty high free throw record. I'm not a basketball fan, so I don't have a name. I usually call on my class to give me a name. Let's just say it's John Smith. So he gets paid millions of dollars to play basketball. Part of that is to stand on the free throw line and throw free throws. He probably makes most of his shots, but not all of them. Even the shots he makes don't go into the basket at exactly the same spot each time. Sometimes they go through without hitting the hoop. Sometimes they hit the hoop on the left, sometimes on the right. Sometimes they bounce off the backboard. So random variation is natural variation in the output of the process created by countless minor factors. So with our basketball player, it could be the temperature in the stadium, any wind in the stadium, just natural variation. So random variation, natural variation, they mean the same thing. Assignable variation is a variation whose source can be identified. So if John Smith has hurt his shoulder, he's not going to be such a good free throw thrower. If you were monitoring that on a control chart, possibly the process would be out of control. So the control chart would tell you that there was assignable variation. It wouldn't tell you what was causing that. It would just tell you there's a problem. So it would be the manager's job, or in this situation, the coach's job, to go figure out what was causing the assignable variation. The job of sampling and putting together a control chart is to test to see whether this non-random assignable variation is present. Sampling ends at that point, or the job of sampling ends at that point. If the sampling indicates that assignable variation is present, management has to go figure out what's causing it and resolve the problem. If there is no non-random variation present, then the process is performing according to its capability. If that doesn't meet what the customer needs, then we've got to look at either bypassing this customer or upgrading our process. Let's look at an example. In this case, the process for filling bottles of a soft drink. And I know there's a can shown on the screen, but that's the only picture I could find in the public domain. If we take samples of a certain size and measure how much soda's in the can, there's going to be variation, even though the process is completely automated. If we're supposed to be putting in 12 ounces, then the values we measure would be clustered around 12 ounces, but they wouldn't be exactly 12 ounces. Some of the cans would have more than 12 ounces, some of them would have less than 12 ounces. Now that's individual bottles or cans. Now we can take a sample and compute a sample mean, say size 10. The sample mean would be clustered around 12, and it would have less variability than the individual cans or bottles. The reason for that is the larger the sample size, the smaller the standard deviation. That's part of the central limit theorem. If there's only random variation, then the distribution that we got would represent the inherent process variation. Additionally, if the sample size is large enough, the distribution of sample means will be normally distributed regardless of the distribution of the underlying process mean. That's just the central limit theorem. These sample means will be used to judge whether a process is performing appropriately. In other words, if it's in control or out of control. Control charts need a z-value from the standard normal distribution. At least most of them do. Some of them are used tables, but those approximate what the z-value would be. Control charts typically use a z-value of 2 or 3. 3 is actually more common than 2. A value of z equal 2 gives you a 95.44% control chart. Remember, z equal 1.96 gives you a 95% confidence interval or control chart. A value of z equal 3 gives you a 99.74% control chart. And remember, a value of 2.576 gives you a 99% one. As I've said before, control charts are used to distinguish between random and non-random variation. In other words, to distinguish between random and assignable variation. They're based on sample means, sample ranges, not on individual observations, although the sample sizes tend to be fairly small. The control limits, the upper control limit and the lower control limit, are the dividing lines between random and assignable variations. Control charts are based on business statistics, specifically confidence intervals. So let's dive back into business statistics for a moment. A type 1 error is concluding a process is not in control when it actually is in control. In quality control, we call that the producer's risk, and it's represented by a value of alpha. That alpha means exactly the same thing as it did in business statistics. A type 2 error is concluding a process is in control when it's actually not in control. We call that the consumer's risk in quality control. We represent that with a value of beta, and we generally don't really know what beta is. Let's look at that graphically. There are 4 possibilities. In reality, it's in control, and we conclude it's in control, so we made the right decision. In reality, it's in control, and we conclude it's out of control. So we scrap a batch of stuff that we produced, even though it's good, because we mistakenly concluded that it was bad. That cost the producer money. That's why we call it the producer's risk. In reality, it's out of control, and we conclude it's out of control. Again, we made the right decision. We scrapped a bad batch. Or, it's out of control. In other words, it's a bad batch, but we conclude it is in control. In other words, we ship a bad batch to the consumer. The consumer gets a bad product, so we call that the consumer's risk. There are 2 types of measurements that we can make, variables and attributes. Variables generate data that can be measured. Your height, your weight, income, diameter of a hole. In other words, they're variables that you can devise an instrument to measure. Attributes are data that are counted. The number of defects, the number of times the shipment was late. In other words, they're not measured with an instrument. We're going to look at 4 types of control charts, 2 for variables and 2 for attributes. There are others, this is not all of them, but these are the 4 that are typically covered in most textbooks. For variables, we're going to look at a mean and a range chart. For attributes, we're going to look at a P chart and a C chart. Regardless of the type of the chart, as I mentioned earlier, finding a control chart is 4 steps. 1, compute the upper control limit. 2, compute the center line. 3, compute the lower control limit. 4, plot the data. If you're working homework, in addition, your professor is going to want you to point out any points that are out of control. For variables, a mean control chart is used to monitor the central tendency of the process mean, in other words. This is displayed using an X-bar chart. There are 2 different ways to compute this. This is the only one where that's the case, but there are 2 different ways to compute it. We will briefly look at both of them. A range chart is used to monitor the process dispersion, in other words, how variable it is. We're going to measure this using an R chart, R short for range, but there's also an S chart, and S is short for standard deviation. Both the mean chart and the range chart require a table. One approach to doing the mean chart uses a standard normal table. The other part just uses a regular table that I'm going to show you in a second. The range chart just always uses the table I'm going to show you in a second. Here's the table for a mean chart and a range chart, but I don't want you to use it. The reason for that is I've shown the parameters with 4 decimal places. Your book may use 2 decimal places, 3 decimal places, or 4 decimal places. I've seen them all. If you use more decimal places or less decimal places than your textbook uses, your answers won't match the instructor's key. Now, if they're looking closely, they'll catch that and they won't count it off, but you never know. If you're submitting it on an online platform like Connect from McGraw-Hill, the computer won't know. These are based on sample sizes, not number of samples. So if you got 10 samples, each of size 5, you would go down and use row 5. That's a common mistake that students make, is to use the number in a sample, the 10 in my example, rather than the 5. So pay close attention to that. The row is based on the number in one sample. For the X-bar control chart, the center line is the grand mean. That's the average of all the sample means. Sometimes it's written as an X with 2 bars over it. There are 2 approaches for finding the upper and lower control limits, using the standard deviation and an equation and a z-value from the standard normal table, or using the factor table I just showed you. We'll look at both of them. Using the standard normal table, the upper control limit is X bar plus z times the standard error, which is X bar plus z times the standard deviation divided by the square root of n. The center line is the grand mean, as I said. The lower control limit is X bar minus z times the standard error, which is equal to X bar minus z times the standard deviation divided by the square root of n. If you're going to use the factor table, then for each sample you need to compute the range. That's the largest minus the smallest. Once you've got those values for each sample, you need to compute the average range. That's R bar. Once you have the average range, the upper control limit is the grand mean plus A2 times the average range. The center line is still just the grand mean. The lower control limit is the grand mean minus A2 times R bar. In other words, the control limits are symmetric about the grand mean, and that's true with either approach. So, which one do you use? Do you use the equation based on the standard normal distribution and the standard error, or do you use the factor table? What I tell my students is, if the standard deviation is given or the standard error is given, then use the first set of equations, the one based on the standard normal distribution. If the standard deviation or standard error is not given, I tell them to use the factor table. The reason I do this is I don't want them spending time in an operations course computing standard deviations. Your professor may feel differently, so ask your professor if your textbook talks about both approaches. As I mentioned, range charts are used to monitor process dispersion. They always use the factor table. They never use the standard deviation approach. Of course, if you got the standard deviation, it would make sense to use the range anyway. You'd use an S chart. The upper control limit is D4 times the average range. The lower control limit is D3 times the average range. Since you're using different values, the range chart will not be symmetric around the average range. So the steps for computing the X bar and R chart are as follows. 1. Find the mean of each sample. 2. Find the range for each sample. Once you've got the mean and the range for each sample, you don't need the raw data anymore. Compute the upper and lower control limits. Draw the chart and plot the data. For all of these control charts, there's a limitation on the approach that most textbooks use. They give you the same data to compute the control limits and construct the chart. Sometimes they want you to see an out-of-control chart, so they give you data that's out of control. But the fact that the data is out of control, because of the mechanics of computing the chart, it forces the upper and lower control limits to be wider than they would be otherwise, which makes it harder for the point to be out of control, so you have to make it more out of control. That's not the way you would do it in real life. In real life, you'd service the machine, make sure everything was in adjustment, you'd get your best operator, you'd run the machine, collect data, and then you would develop a control chart based on that optimized data. Then you would never change your upper control limit, center line, lower control limit unless the process changed. After that, you just collect the data and plot it on the chart. That way, anything that was out of control would tell you that the process was not doing as well as it could be under optimum circumstances. Almost all of the charts that the textbooks give you suffer this problem. The only one that doesn't is the X-bar chart when they give you the standard deviation. Since they're giving you the standard deviation rather than computing it on the data they give you, they can give you a smaller standard deviation based on what the process should be, and you'd have out-of-control points. All the others have this problem. There's nothing you can do about it. It's just an observation I'm giving you. You always use the X-bar and R chart together. You never just use one. To be more specific, since you might not always use the R chart, you might use an S chart, you always use an X-bar chart and a chart that measures dispersion together. The X-bar chart will tell you if the mean shifts, but it won't tell you if the dispersion changes. An R chart, or an S chart, will spot changes in the dispersion, but will not tell you if the mean shifts. That's why you have to use them together. Now let's look at control charts for attributes. We're going to look at 2, the P chart and the C chart. Students oftentimes confuse these two, so pay particular attention to the difference. A P chart is a control chart used to monitor the proportion of defects in a process. With a P chart, you look at each item and you say, defective, good, defective, good. In other words, it's digital. Each item can only have 2 outcomes, good or bad. A C chart is a control chart used to monitor the number of defects per unit. So that's only possible when you can have more than one defect per unit. I'll give you examples of when you'd use a C chart in a moment. I just want to make that distinction before we move on. So as I said, use a P-chart when observations can be placed into two categories: good, bad, pass, fail, works, doesn't work. With a P-chart, you're going to have multiple samples, and you're going to compute the proportion of defects in each sample. With a P-chart, you typically don't know the population proportion. So you're going to take samples of P and use the average P-value as the stand-in for the population proportion. So you're using P-bar in all the formulas. I'm showing the formula in two parts: the standard error and then the upper and lower control limits. Some textbooks will just put these together. Standard error is equal to the square root of P times 1 minus P divided by N, the size of one sample. Some textbooks use Q instead of 1 minus P. The upper and lower control limits are computed as the sample proportion plus and minus the z-value, which is usually 2 or 3, times the standard error. There are two very important points about P-charts. One, you must be careful with the decimal points. And by careful, I mean you need to carry enough decimal points. The proportion of defect tend to be small, 1%, 2%, and that gives you a very small standard error of the proportion. I've seen problems where the answer can vary greatly depending on how many decimal points the students use. So I always tell my students to carry at least 4 or 5 decimal points. 2, it is possible with the calculations to have the lower control limit to be negative. That is not allowed. With quality control, you could never have a negative number. You can't have less than 0 proportion of defects. So when the lower control limit calculates out to be a negative number, you just make it 0. Let's talk about C-charts. C-charts are used when an item can have more than one defect. It's called a C-chart because we count the number of defects that each item has. So this could be the number of scratches and dents on a car, the number of mistakes that a cleaning person made cleaning a motel room. It could be the number of bacteria in a sample. It could be the number of calls of complaints you got. Lots of things. I have seen students try to make these into P-charts, but you can't. Don't even try that. You get the wrong answer. If an item can have more than one defect, it's always a C-chart. For a C-chart, the upper control limit is the average number of defects plus Z, which is normally 2 or 3, times the square root of the average number of defects. The lower control limit is C bar minus Z times the square root of C bar. As I said, C bar is the average number of defects per unit, and the center line will also be C bar. C-charts are even more likely to have negative lower control limits than P-charts, and again, if the lower control limit is negative, you make it 0. Statistical process control was developed for manufacturing and has historically been used primarily in manufacturing. It is starting to migrate to services. However, it's hard to use it in services on things that matter the most. Think about a restaurant. The thing that matters most to the customers: does the food taste good? That's not something you can measure. So we default to measuring things that are easy to measure. Wait time, on-time delivery, things that are easy to measure. So we're monitoring things that might matter to the customer, but typically we can't monitor the things that matter the most to the customer. That's not always the case. There are some services where you can do that, but it's fairly common that you can't measure the most important thing about the service. But we can still get useful information. Many years ago, I was elected to the city council of a city. The city councilman had different jobs, and my job was to be chairman of the police oversight committee. I suggested to the chief that we should start monitoring our crime statistics using control charts. Police collect a lot of statistics in fairly standard format because it has to be reported to the FBI that way. He was reluctant at first, but we ended up doing that. Not only that, we posted the control charts out in the lobby of the police station so our citizens could see how well or poorly we were doing. The chief ended up really liking the control charts. The reason why is about a year later, there were a rash of car break-ins. He would have eventually spotted that looking through the numbers in the reports, but it popped out so quickly in the control chart. Now, it told him that there were a higher number than average car break-ins. It didn't tell him where it was happening or why it was happening. So he had to dig into the numbers to see where it was happening. Then they did a stakeout. They found some teenagers who were breaking into the car to look in the glove box for things that they could sell. So they caught the bad guys, and they caught them quicker because they had control charts. So you can use it in services, and you can collect meaningful data. This also points out a very important consideration with control charts. If you're monitoring crime, you only care about the upper control limit. That's not really true. Let me restate that. You mostly care about the upper control limit. In the case of the car break-ins, the number of break-ins exceeded the upper control limit, and they went and investigated the situation and caught the bad guys. That was the primary use of the crime control charts that we used. And like I said, you mostly care about the upper control limit. But the lower control limit can tell you something too. If you consistently get a value that's low, then that tells you you're doing something right, and you want to look into it to see what you're doing right. But mostly you care about the upper control limit. So there are situations, more in services than in manufacturing, where you only care about either the upper control limit or the lower control limit, but not both. Producing a control chart requires collecting a sample and making a measurement. That's not free. That takes time and testing, and if the test is destructive, it destroys products. It's not always destructive, but it could be. So a big decision is at what point or points do you want to collect the data and put together a control chart. The next decision is how large of a sample do you want. Sample sizes tend to be in the 5 range. They're not large. And then a third decision is what type of control chart to use, whether it's variable or attribute. That's really more driven by the type of data that you're able to collect. Variable data is more meaningful, it's more useful. So if you've got the option, you'll collect variable data, but a lot of times you don't have that option, so you end up collecting attribute data. In addition to looking for points that are above the upper control limit or below the lower control limit, there are other things that we can look for. One is a trend, and a trend is actually fairly common. So if you're measuring the size of a hole that you're drilling and the drill bit starts getting dull, it's going to drill larger holes because it's going to wobble. You can see that as a trend. That allows you to change the drill bit before the holes get too large. You can look for cycles where things go up and down and up and down. That could be operator error, could have a lot of causes. You can look for bias, where more of the points are above the center line or more below the center line. You can look for a mean shift that's been at 1 inch, 1 inch, all of a sudden it's at 1.1 inches. And you can look for too much dispersion. Looking for above the upper control limit or below the lower control limit is not really enough. In terms of the observations, we would expect about 2.56% to be in the yellow. We would expect a little over 27% to be in the blue. And we expect a little over 70% to be in the green. So we expect most of the observations to be near the mean. If you're seeing too many towards the upper or lower or both control limits, that's a problem. Typically too much dispersion. Control charts tell you that you have non-random variation, assignable variation, but they don't tell you why. Managers have to investigate and figure out what the problem is. It is possible, not likely, but possible that you have a false alarm, particularly if it's just 1 point. Remember that type 1 error. More likely, you've got assignable variation. If you've got assignable variation, you've got to figure out what's causing it, and then you've got to resolve the problem. If you enjoyed this video, please click like and consider subscribing to this channel.